Madam, please start.
Yeah. Good morning, everyone, and good morning, dear students. Once again, a happy welcome to the chemistry webinar. So, it's my privilege to welcome Mrs. T. Madhavi, PGT Chemistry from TSMS Pudu, and myself, Mrs. Sridevi Polu, Principal, TSMS Pudu. It's privileged to be a part of this. And dear children, in our yesterday's session, Mrs. Madhavi has taught you the 16th group elements. She has introduced you the family. What is that family? Chalcogen's family, oxygen family. Oxygen, sulfur, selenium, tellurium, and polonium. And a new element was introduced, livermonium, isn't it? And ma'am has very clearly explained you regarding the properties. What is the properties? Periodic properties of the 16th group elements and why they are called as chalcogens and what happens to the periodic properties down the group, right? So, and you should remember here about oxygen, children. See, it is the second most electronegative element present in the periodic table. And what is the first element which is having highest electronegativity? It is fluorine with a value of 4.0, isn't it? So today ma'am is again here. Good morning, Madhavi ma'am.
Good morning, ma'am.
Please welcome. And today you are going to explain what topics, ma'am?
About oxygen and ozone, ma'am. Their properties, preparation, molecular structure, uses, all these
Okay.
things we are going to discuss. Very important. Ozone is very important for their examination.
Okay. Okay, ma'am. And dear children, today ma'am is going to explain you regarding the allotropes of oxygen, right? So ozone is the allotropic form of oxygen. Oxygen is O2, isn't it? And O3 is ozone. And she is going to explain you what is ozonolysis, right? So ozonolysis, adding of ozone, and lysis means breaking. So the compounds which contain double bond and triple bond. And what are those compounds called as? Unsaturated hydrocarbons reacts with ozone and form ozonide. And this on hydrolysis gives carbonyl compounds. And ma'am is going to explain you about all these things. And let's not waste the time. So it's my pleasure to welcome Madhvi ma'am. So I would like to hand over the session to Madhvi ma'am.
Thank you, ma'am. Thank you.
Yeah. Thank you, ma'am.
Good morning, everyone. Welcome back to second session on 16 group elements. Now let us have a quick review. What are topics that we have covered in the previous session? So in that we have discussed about atomic properties of 16 group elements. What are 16 group elements? Oxygen, sulfur, selenium, tellurium, polonium, and livermorium. So in that we have discussed atomic properties, electronic configuration. What is the general electronic configuration? NS2, NP4 is the general electronic configuration of 16 group elements. So 16 group elements are also called as chalcogens that we have discussed in the previous session, is it not? So how many valence electrons that the 16 group elements are having? 6 valence electrons, 2 electrons in s orbital and 4 electrons in p orbital, right children? So next, after that, we have discussed atomic and ionic radii. So from top to bottom, in a 16 group elements, number of shells are goes on increasing. So that's why atomic and ionic radii top to bottom increases, right? So after that, ionization enthalpy. What is ionization enthalpy? The amount of energy that is required to remove an electron from an isolated gaseous neutral atom. Is it not? So ionization energy enthalpy is inversely related to atomic and ionic radii. So top to bottom, atomic and ionic radii increases, so ionization enthalpy decreases, right? So after that, we have discussed electron gain enthalpy. So what is electron gain enthalpy? The change in the amount of energy when an electron is added to an isolated neutral atom. So in that case, the change may be increase or decrease, but in 16 group elements, it is increase in energy, means energy will release. So that's why electron gain enthalpy for 16 group elements is negative. So this electron gain enthalpy is also inversely related to atomic and ionic radii. So top to bottom, electron gain enthalpy decreases because atomic size increases. But here one point you have to remember, very important point. sulfur is having high electron gain enthalpy when compared with oxygen. So this is due to compact size of oxygen, because if you add one electron to the oxygen, then what happens? Repulsion between the electrons will take place, because size of oxygen is very small, because second shell is the outer shell for it. Okay, whereas in case of sulfur, the size is neither too small not too big, so if you add one electron to it, it easily accepts that electron. So that's why electron gain enthalpy for sulfur is more when compared with oxygen. Next, electronegativity. The ability of an atom to attract the bond pair of electrons towards it is called as electronegativity. So this is also inversely related to atomic and ionic sizes. So what happens? Electronegativity, top to bottom atomic size increases, so electronegativity decreases. So as ma'am said, oxygen is the second most electronegative element in the periodic table. So which one is the highest electronegative element? Fluorine is the highest electronegative element. Okay, so in 16 group, oxygen is there, so it is the high electronegative element in that group, right? Next, in physical properties, what we have discussed, oxygen and sulfur are non-metals, and selenium, tellurium are metalloids, and polonium is a metal, and livermorium is a synthesized element, right? So next, top to bottom, electronegativity decreases, so metallic character increases. Next, in chemical properties, what we have discussed in the previous session, oxidation states and trends in chemical reactivity in that. So oxygen shows -2 oxidation state because it is a highly electronegative, but whenever it combines with fluorine, it shows a +2 oxidation state. Okay, remaining elements can able to show +2, +4, and +6 oxidation states also. But +6 oxidation state stability decreases from top to bottom because of inert pair effect that we have discussed in the previous session, children. Next, reactivity towards hydrogen, they can able to form uh, H2E type of hydrates. Next, they when they react with oxygen, they can able to form EO2 and EO3 type of oxides they will form. Okay, so next, reactivity towards halogen, so they can able to form EX2, EX4, and EX6 type of halides, where E is element of 16 group element, and X is halogen, right, children? So these things we have discussed in previous session. Now let us see what are the subtopics that we are going to cover today. Let us see dioxazine. So dioxazine and its preparation, properties, uses will discuss. Simple oxides. Next, ozone preparation, properties and structure of ozone and its uses. So these are the subtopics that we are going to cover today. So now let us start today's session quickly. Dioxazine. So what is the formula for dioxazine? O2, right, children? Okay, so dioxazine, so it is very, very important for our life, right? So how to prepare this dioxazine? So first one is laboratory method. So this dioxazine can be prepared when salts containing oxygen like chlorates, nitrates, and permanganates, when they are heated in presence of some catalyst like manganese dioxide, they can able to give oxygen. For example, potassium chlorate, KClO3, when it is heated in presence of manganese dioxide, it gives KCl plus oxygen. Three molecules of oxygen will get when two molecules of KClO3 is heated, right, children? So this is the laboratory method. You can see the setup for the preparation of oxygen by KClO3 decomposition. Now see here, this test tube is having potassium chlorate along with the small quantities of catalyst manganese dioxide. So when it is heated, oxygen is released. So that oxygen is passed through this water and it is collected in this container, right, children? So this is the oxygen. So this is light in weight, so that's why it will collected here, right, children? So this is the methods of preparation of oxygen by KClO3 or nitrate or permanganate salts, right? So this is the laboratory method. Now coming to the next method, this is also a laboratory method only. Thermal decomposition of oxides of metals low in the electrochemical series. So which metals are present in low in the electrochemical series? Which are less reactive metals. So their oxides on thermal decomposition. What is thermal decomposition? By heating. So in presence of some catalyst, so these oxides on a decomposition, thermal decomposition, they give oxygen. For example, Ag2O, okay, silver oxide. So when it is heated, it gives a silver plus oxygen. Similarly, mercuric oxide, so HgO, when it is heated, oxygen is liberated, right children? So another method is, so on thermal decomposition of higher oxides of some metals. So see here, Pb3O4, PbO2. So these are higher oxides. When these higher oxides on thermal decomposition also gives oxygen. So these are the laboratory methods. Okay. So salts of KClO3 means potassium chlorate, potassium permanganate, potassium nitrate. So which are having oxygen, when they are heated in presence of in presence of a catalyst, they give oxygen. And on thermal decomposition of oxides of metals low in the electrochemical series gives oxygen. And higher oxides of some metals on thermal heating, they give oxygen. Okay. Next, coming to hydrogen peroxide. You know that children, H2O2 is a hydrogen peroxide. So hydrogen peroxide readily decomposes into water and dioxygen by catalysts such as finely divided metals and manganese dioxide. So in presence of a finely divided metal and manganese dioxide as a catalyst, so this hydrogen peroxide, it readily decomposes to give oxygen and water. H2O2 to H2O2 is gives rise to H2O plus O2, right children? So this is a also decomposition, right, in presence of finely divided metals and manganese dioxide. They acts as a catalyst. Okay. So next one, on a large scale, it can be prepared from water or air. So industrially, it can be prepared by the electrolysis of water, or by fractional distillation of air. We can able to prepare oxygen. So first let us see how this oxygen is prepared by electrolysis of water. So you know that children, the formula of water is H2O, right? So when acidified water, we have to take and we have to pass current through it. Okay. So this is anode and this is cathode, children. So these are the metal rods. If you pass electricity through it, through a solution of acidified water. Why we have to take acidified water? Because pure water is a bad conductor of electricity. To conduct electricity, free ions are required. So that's why little quantity of acid is added to water to increase its conductivity. So that's why acidified water, when it is electricity is passed through the acidified water, then what happens? Oxygen is collected at anode and hydrogen is collected at cathode. You can see children here, hydrogen and oxygen volume. So hydrogen volume is double when compared with the volume of oxygen, is it not? So that's why hydrogen and oxygen, because H2O, two volumes of hydrogen and you will get one volume. So hydrogen and oxygen are in the ratio of 2:1. Okay. So can be collected at anode and cathode. So now we are our concentration is only for the preparation of oxygen. That's why anode is collected at oxygen oxygen is collected at anode by electrolysis of acidified water. Okay. So children, so from lower classes itself, you are learning about this electrolysis of water gives oxygen and hydrogen. Next one is industrial method. So that is nothing but from air. So you know that children, air consists of 21% of percent oxygen and 78% nitrogen and 0.03% carbon dioxide and water vapor, and remaining gases like argon and all are present. Okay. So from that 21% of oxygen is there. So from that we can able to collect oxygen. Okay. So now let us see how how to prepare oxygen by from air. So first, removing carbon dioxide and water vapor. First, what we have to do, we have to remove carbon dioxide and water vapor, and after that, what we have to do, we have to liquefy the air. So how to liquefy the air? Just simply compressing and cooling will get liquefied air. So after getting liquefied air, so that can be done fractional distillation. After doing fractional distillation, we can able to get liquid oxygen, right children? So here, so this is the method. So compression of air, so and then it is cooled, and it is carbon dioxide is separated, and then liquid air is fractional distillation. After fractional distillation, it gives uh, nitrogen and argon here, and liquid oxygen here. So at the end we'll get liquid oxygen. So this is the method to prepare dioxygen from air, right children? Next. So now these are the methods of preparation of dioxygen. Now coming to the properties of oxygen. So we know that dioxygen is a colorless, odorless gas. So its solubility in water is to the extent of 3.08 centimeter cube in 100 centimeter cube water at 293 Kelvin, which is just sufficient for the vital support of marine and aquatic life. Okay children, so 10 centimeter cube volume of water, in that 3.03 centimeter cube of a volume of oxygen can able to dissolve. So that dissolved oxygen is at 293 Kelvin. Temperature is very important. So if you change the temperature, then this volume of oxygen changes. Okay, so at 293 Kelvin, 3.03 centimeter cube of oxygen, volume of oxygen can able to dissolve in 100 centimeter cube of water. So that is very important for, which is sufficient for vital support of marine and aquatic animals. Okay, so next one, it liquefies at 90 Kelvin and freezes at 55 Kelvin. Okay, so that's why at room temperature, it is in gaseous state, right children? So it liquefies at 90 Kelvin and freezes at 55 Kelvin. Next, coming to oxygen, it is having three stable isotopes. What are isotopes? Having same atomic number but different mass number. You can see here atomic number is 8 only for all the three isotopes, but mass number is 16, 17 and 18. Oxygen is having three stable isotopes. So O16, O17, O18. Next, molecular oxygen is paramagnetic. We know children in first year you have, so molecular orbital theory. Why oxygen is paramagnetic in nature? Because it is having unpaired electrons in 2px and 2py, pi star 2px, pi star 2py. So these are anti-bonding molecular orbitals, pi star 2px and pi star 2py. They are having unpaired electrons. So any substance, if it is having unpaired electrons, it is paramagnetic in nature. So oxygen is having unpaired electrons in pi star 2px and pi star 2py. So that's why oxygen is having paramagnetic nature. So it will attract towards the magnetic field, right children? So next one, dioxygen is directly reacts with nearly all metals and non-metals. So oxygen it combines with nearly all metals and non-metals, but except some noble metals like gold and platinum. So these are noble metals because their reactivity is very less. So oxygen, it cannot react with some noble metals like gold and platinum, and some noble gases. Some noble gases also it cannot react, right children? So next, the bond dissociation enthalpy of oxygen double bond is high because there is a double bond between oxygen and oxygen. So high bond dissociation enthalpy is required because size of the oxygen atom is also very small, and there is a double bond between two oxygen atoms. So the bond length is very less between two oxygen atoms. So that's why bond dissociation enthalpy is very high. That is 493.4 kilojoules per mole, right children? So what are the things that we have discussed? So oxygen is having three isotopes, O16, O17, O18. Water isotopes having same atomic number but different mass number. So molecular oxygen is paramagnetic because it is having an anti-bonding molecular orbitals like pi star to px and pi star to py. So single electrons are present, unpaired electrons are present. So that's why it is a paramagnetic in nature, weakly attracted towards the magnetic field. So dioxygen, it can able to react with all metals and non-metals except some metals like noble metals, gold and platinum, and with noble gases. Okay, some noble gases. Next, bond dissociation enthalpy. So oxygen in between double bond is present, and the bond length is also very small because oxygen is very small atom. So that's why 493.4 kilojoules per mole energy is required to break the bond between two oxygen atoms. Okay, so we just now only we have discussed that oxygen can able to combine with many metals and non-metals except noble metals, is it not? So it can able to react metals and non-metals. Now let us see some reactions. Calcium, when it reacts with oxygen, gives calcium oxide. So aluminium, when it reacts with the oxygen, gives aluminium oxide. So oxygen is combining with the metals. Calcium and aluminium are metals, so they give metallic oxides. Similarly, oxygen can able to react with the non-metals. So phosphorus is a non-metal, carbon is a non-metal. So when oxygen combines with the phosphorus, gives P4O10. Okay, and carbon, when oxygen combines with the carbon, so carbon dioxide. So these two reactions are reaction of oxygen with metals, and these two reactions gives a reaction of oxygen with the non-metals. Okay, now not only with the metals and non-metals, so it can also combine with it also reacts with some compounds. So for example, zinc sulfide, when it reacts with zinc sulfide oxygen, it gives zinc oxide and sulfur dioxide. Okay, and when it reacts with methane CH4, when oxygen reacts with methane, it gives carbon dioxide and H2O. Okay, so from these reactions what we have understood, so oxygen, it can able to react with metals, non-metals, and other compounds also except noble metals and some noble gases, right children? Next, some reactions, they are means combining with oxygen is nothing but it is an oxidation reaction. So some reactions, they are catalytically oxidized. Some compounds are catalytically oxidized. For example, SO2, when it reacts with oxygen, so V2O5 acts as a catalyst. So it gives SO3. So children, this reaction is very important. So one of the step in preparation of sulfuric acid by contact process, sulfur dioxide, when reacts with the oxygen in presence of vanadium pentoxide, it gives sulfur trioxide. Okay, next, when HCl reacts with oxygen and gives in presence of a copper chloride, CuCl2 gives chlorine and H2O. So this reaction is also very important. So this is the method of a preparation of a chlorine. So we'll discuss in a Decon's process. So in Decon's process, HCl combines with the oxygen in presence of copper chloride, gives chlorine plus H2O. So some compounds are catalytically oxidized. It means to combine with oxygen, they required some catalyst. So in the first case, vanadium pentoxide is used as a catalyst, and in second case, copper chloride is used as a catalyst. So these are the reactions of oxygen with metals, non-metals, and with some compounds. Now let us see the uses of oxygen. So children, very important for animals and human beings. So oxygen is very important. So for life, oxygen is very important. So green plants, they give oxygen, is it not? So oxygen is very important for us. So let us see other uses of oxygen. Okay, so oxygen is used in oxyacetylene welding. So oxyacetylene welding means acetylene and oxygen, when they combine and they undergo combustion. So so that method is used for the high heat is produced. So that is used for the welding purpose. So this oxyacetylene welding, so this is also used in the manufacture of many metals, particularly steel. Okay, so oxygen is very very important in that case for welding purpose, for the preparation of many metals like steel. Oxygen is very important. Next use, so we know that oxygen cylinders are widely used in hospitals, altitude flying, and in mountaineering. So very important nowadays in this pandemic situation, this oxygen, so very very important, is it not? Ventilators, so these are very important. So oxygen cylinders are widely used in hospitals. Altitude flying means that is trekking and all. Next, mountaineering. So climbers, they use this oxygen because at the high altitude the percentage of oxygen will be less. So in that case, these oxygen cylinders they carry. So very important, children. Next, after that. So combustion of fuels, so the combustion of fuels, hydrogen, for example, if you consider hydrogens in liquid oxygen provides a tremendous thrust in rockets. Okay, liquid oxygen. So hydrogen in liquid oxygen is provides a tremendous thrust in rockets. So for combustion of all fuels, oxygen is required. So oxygen is a supporter of combustion. So in presence of oxygen only combustion will takes place. So combustion process is a highly exothermic process, is it not? So it, for example, hydrogen in liquid oxygen provides a tremendous thrust in rockets. Okay, children. So these are the uses of dioxygen. Next, coming to some simple oxides. So what are oxides? Binary compound of oxygen with another element is called as oxide. Okay, so these oxides, you know that oxygen reacts with most of the elements of the periodic table except some noble metals and some noble gases. Even with some noble gases also it can able to react. Krypton and xenon also oxygen can able to react. So some like helium and neon oxygen cannot react. So noble metals like gold and platinum and some noble gases oxygen cannot react, but remaining most of the elements they can able to react with oxygen, they can able to form oxides. So these oxides are different properties they are having, their nature and properties are different. So oxides can be simple oxides and mixed oxides. So for example, magnesium oxide and Al2O3, these are simple oxides, and mixed oxides means Pb3O4, Fe3O4. So this is the mixture of Fu and Fu2O3, is it not? So that's why it is called as mixed oxide. Okay, so but our concentration is on simple oxides. Now we are going to discuss about only simple oxides. So again, the simple oxides are classified into three categories. One is acidic, basic, or amphoric. Depending upon their nature, the simple oxides are classified into acidic oxides, basic oxides, or amphoric oxides. Now let us see one by one. So an oxide that combines with water to give an acid is termed acidic oxide. So what is acidic oxide, children? So whenever that oxide is mixed with or combines with the water to give an acid, that oxide is called as acidic oxide. For example, SO2, Cl2O7, CO2, N2O5. So all these are acidic oxides. Okay, for example, if you consider SO2, when it combines with water, it gives S2, H2SO3. What is H2SO3? Sulfurous acid. Okay, H2SO3 is a sulfurous acid. Similarly, SO3 is also acidic oxide. SO3 plus H2O gives H2SO4. Okay, so these oxides, when they combine with water, they give acids. Okay, such oxides are called as acidic oxides. Okay, mostly non-metal oxides are acidic oxides. You can see here sulfur dioxide, yes, is sulfur is a non-metal. Chlorine is a non-metal. Carbon dioxide, carbon is a non-metal. In nitrogen pentoxide, nitrogen is non-metal. So non-metal oxides are having acidic in nature. So not only non-metal oxides, metals in metal oxides in a high oxidation state also have acidic character. For example, Mn2O7. So manganese, Here, what is the oxidation state of manganese? +7 is the oxidation state of manganese. So high oxidation state it is having. Even chromium trioxide, what is the oxidation state of chromium? +6 is the oxidation state. And even V2O5, vanadium pentoxide. So vanadium is having +5 oxidation states. So metal oxides in a high oxidation state also have acidic character. Not only non-metal oxides are having acidic character, but also metal oxides which are in a high oxidation state like MnO7, Mn2O7, CrO3, V2O5. In these metals are having a high oxidation state, so they can also show acidic character. Next, coming to the oxides which give a base with the water are known as basic oxides. We know, children, um, oxides which combines with water give acid are called as acidic oxides. Now oxides which combine with water to give base are called as basic oxides. Very simple thing, is it not? So for example, Na2O, CaO, BaO. So sodium oxide, calcium oxide, barium oxide. So these are having a basic in nature. Why they are having basic in nature? When they combine with water, they give base. For example, calcium oxide, when it combines with water, gives calcium hydroxide. So CaO plus H2O is gives rise to CaOH twice. So CaOH twice is a base. Okay, so that's why calcium oxide is a basic oxide. Okay, so mostly metallic oxides are basic in nature. All metallic oxides, when they combine with water, they give base. So that's why metallic oxides are basic in nature. Okay, children. So calcium oxide is a basic in nature because calcium oxide, when they combine with water, gives calcium hydroxide, which is a base. Is it clear, children? So very simple thing. Next one is some metallic oxides exhibited dual behavior, means they can able to behave as acid as well as a acidic in nature as well as basic in nature. Such oxides are called as amphoteric oxides. Okay, children. So they show characteristic of both acidic as well as basic oxides. Such oxides are known as amphoteric oxides. Means they can able to show acidic nature as well as basic nature. Such oxides are called as amphoteric oxides. For example, aluminium trioxide Al2O3 is a amphoteric oxide because it can able to it is having both acidic as well as a basic nature. For example, Al2O3, when it reacts with HCl in presence of water, it gives AlH2O6 3 plus. It is a complex hexa aqua aluminium 3 ion plus 3Cl minus ions. So this is it means Al2O3 is combining with acid. It means it is having basic in nature, right? Next, similarly, Al2O3 is combining with sodium hydroxide with base in presence of water and gives Na3AlOH6, means sodium hexahydroxo aluminate. So this is a complex compound, right, children? So in this, from these two reactions, so what we have observed, aluminum trioxide, it is reacting with the acid. Aluminum trioxide, it is also reacting with the base. It means that it is having both acidic and basic nature. That's why aluminum trioxide is a amphoteric oxide, right, children? Okay, next, coming to, there are some oxides which are neither acidic nor basic, means they are not showing even acidic nature or even basic nature, whereas amphoteric oxides, they are showing both acidic nature and basic nature, like aluminium trioxide, it is combining with acid as well as base. That's why it is amphoteric oxide. But there are some oxides, they cannot show, they are neither showing acidic nature nor showing basic nature. Such oxides are known as neutral oxides. For example, carbon monoxide and nitric oxide and nitrous oxide. So these are not having even acidic nature and or basic nature. So they are neutral in nature. Okay, is that clear, children? So this is about simple oxides. Simple oxides, acidic oxides, basic oxides, amphoteric oxides. Acidic oxides are nothing but, so they combine with water and they give acids. For example, non-metal oxides are having acidic oxides and metals in their high oxidation state also they can show acidic nature. Whereas basic oxides are nothing but they are when they are combined with water they give base. So metal oxides are having a basic in nature. So there are some oxides which are having both acidic character as well as basic character. Such oxides are called as amphotic oxides, like aluminum trioxide. So there are some oxides which are neither having acidic nature nor having basic nature. Such oxides are called as neutral oxides. Example: carbon monoxide, nitric oxide, and nitrous oxide, CO, NO, and N2O. Right, children? Next, coming to ozone. So you know that, so this is the allotropic form of oxygen. You know, children, what is allotropy? So existing an element in more than one physical form is called as allotropy. Ozone is the one of the allotropic form of oxygen. So ozone, so what is the formula of ozone? O3. So dioxygen and O3. So oxygen exists as ozone and dioxygen. Next, coming to ozone. So ozone is an allotropic form of oxygen. So it is too reactive to remain for long in the atmosphere at sea level. You know, children, ozone is also very important. So at a high height of about 20 kilometers, it is formed from atmospheric oxygen in the presence of sunlight. Okay, so in presence of sunlight, oxygen converts into ozone. So in stratosphere, this ozone, it protects us from harmful UV radiations. Okay, this ozone layer protects the earth's surface from the excessive concentration of ultraviolet radiations. It is acting like a blanket. It is protecting the earth's surface from ultraviolet radiations, is it not? Okay, so now let us see how to prepare this ozone in the laboratory. So naturally it is forming in a high altitude, that is in stratosphere. In presence of sunlight, oxygen is converting into O3. So even in a laboratory also ozone can be prepared. So how to prepare this ozone? When a slow dry stream of oxygen is passed through a silent electric discharge, very very important, silent electric discharge, conversion of ozone to oxygen to ozone occurs. Okay, why we need silent electric discharge? Because this ozone, it you can see here, children, 3O2 is gives rise to 3O3. Okay, so 3O2 is gives rise to, when the stream of oxygen is passed through the silent electric discharge, it gives ozone. If you see the change in enthalpy, that is plus 142 kilojoules per mole. Okay, so change in enthalpy is positive, means it is an endothermic process. Energy is required. So this O3 formed, it can able to decompose easily and give oxygen. So that's why what we have to do, we have to prepare this O3 by silent electric discharge, because O3 can able to convert easily into O2, right? To prevent its decomposition, silent electric discharge is necessary. Okay, so very very important, children. Ozone, how to prepare ozone? When a stream of oxygen is passed through a silent electric discharge, conversion of oxygen to ozone occurs. So O2, 3O2 is gives rise to 3O3. Delta H naught is equal to plus 142 kilojoules per mole. So this method is called, the product is called ozonized oxygen. O3 is called as ozonized oxygen. So this is an endothermic process, because plus 142 kilojoules mole energy, okay, is required to convert oxygen to O3. To prevent its decomposition, silent electric discharge is necessary. Okay, now coming to the properties. So pure ozone is a pale blue gas, dark blue liquid. So when it is liquefied, it converts into dark blue liquid, and when it is converted into solid, so it is a violet black solid. Right, children? Okay, so ozone has a characteristic smell. In small concentration it is harmless, but if concentration rises above about 100 parts per million, so 100 ppm, so breathing become uncomfortable, resulting in headache and nausea. Okay, so ozone is a pale blue gas, dark blue liquid, and violet black solid. So it is having a characteristic small smell. So small concentration, it is harmless, but if it concentration rises to 100 parts per million, then what happens? Breathing become uncomfortable and headache and nausea occurs, right, children? Now coming to other properties. So as we have discussed, this ozone easily decomposes to give oxygen and nascent oxygen. This is the nascent oxygen, children. So which is kept in square brackets, means what is nascent oxygen? Is the atomic oxygen. So because of the liberation of this nascent oxygen, O3 is a powerful oxidizing agent. Okay, so it can able to oxidize sulfide to sulfate and iodide to iodine. You can see the reactions here. Lead sulfide when reacts with ozone gives lead sulfide plus oxygen. Okay, so here what happened? It has oxidized sulfide to sulfate, right? So what is the oxidation state here? For sulfur plus minus 2, and whereas in this case it is plus 6, right? So the oxidation state is increased, is it not? So increase in oxidation state is called as oxidation. So O3, it acts as a oxidizing agent, right, children? Next, coming to iodide to iodine. So what is the oxidation state of iodide? Minus 1. For ions, the charge is itself its oxidation state. So minus 1. So minus 1 to 0, for it is an element. So minus 1 to 0, increase in oxidation number. So that's why it is an oxidation, right? So O3, when iodide, it reacts with ozone, it converts into iodine. Okay, oxidation has been taken place. Okay, so in PbS, sulfur oxidation state is minus 2, whereas in case of PbSO4, oxidation state of sulfur is plus 6, right, children? So that's why minus 2 to plus 6, there is an increase in the oxidation number, right, children? So next, coming to another quantitative estimation of ozone. So how to estimate ozone, children, quantitatively? So how much amount of ozone is present, we can able to estimate. Okay, so this is the method. So when ozone, just now only we have discussed, ozone, it reacts with iodide ion, it can able to liberate iodine, is it not? So the amount of iodine that is liberated, if you estimate the amount of iodine that is liberated, you can easily calculate the amount of O3 present in it, is it not? So when what is the procedure? Let us see. When ozone reacts with an excess of potassium iodide solution buffered with a borate buffer, means pH it will be maintained at 9.2, then if you react ozone with potassium iodide, then what happens? Iodine is liberated. So this depends on iodine liberation, it depends upon the amount of ozone, is it not? So one molecule of O3 can liberate one molecule of iodine. So O3 it liberate iodine. If you calculate the iodine liberated, then you can automatically you can able to calculate the amount of O3 present in it. So this is the quantitative estimation. So now see here, after liberating iodine, how to identify, how to calculate the amount of iodine? So it can be done by titrating with sodium thiosulfate. So see children, this is sodium thiosulfate. Iodine liberated can be treated with sodium thiosulfite, okay, sulfate, and it gives sodium tetrathionate plus sodium iodide. Okay, so by this method we can able to estimate ozone, right, children? Okay, again I'm repeating, when ozone reacts with excess of potassium iodide solution buffered with a borate buffer, iodine is liberated, which can be titrated against a standard solution of sodium thiosulfate. This is a quantitative method for estimating O3 gas. When it reacts with potassium iodide, excess of potassium iodide is taken, and when it is react with ozone, it gives iodine. 2I minus plus H2O plus O3 is gives rise to 2OH minus plus I2 plus O2. Okay, so whatever the iodine is obtained in the first reaction, that can be titrated against the standard solution of sodium thiosulfate, that is Na2S2O3. It gives sodium tetrathionate plus sodium iodide. So we can able to calculate the iodine liberated. So by that, ozone present in it can be calculated. So this is the quantitative estimation for the calculation of O3 present. Next one, nitrogen oxides. So mainly nitrogen monoxide combine very rapidly with ozone and gives oxygen. So nitrogen oxides. So from where they are obtaining this nitrogen oxides, emitted from the exhaust system of supersonic jet aeroplanes. So the supersonic jet aeroplanes, they are releasing oxides of nitrogen in the stratosphere. So the oxides of nitrogen, they are combining with the O3. So then what they are doing, they are liberating nitrogen dioxide plus oxygen. They are converting O3 to oxygen. So that's why ozone layer depletion is taking place. So this is the one of the reason for the depletion of ozone layer. One more reason, you know, that very important reason, that is another threat to this ozone layer is the use of freons which are used in aerosol sprays and as refrigerants, fluorochlorocarbons which are uh, refrigerants they are used. Okay, so like ACs, next refrigerators, so they and aerosol sprays, these fluorochlorocarbons are we are using, so they are entering into the stratosphere and they are depleting the ozone layer. So all these things we know, children. So that's why ozone is very important, because it is protecting us from harmful UV radiations. So we should be very careful. So the usage of these fluorochlorocarbons should be reduced or avoided, right? Next one, structure of ozone molecule. We know that the formula of O3 is ozone is O3. So there is a double bond between one oxygen and single bond between one oxygen. But through the spectroscopy, when it is observed, so the bond length in between these two oxygens and these two oxygens is identical. That is 128 picometers. So it shows that so this double bond is not fixed between these two oxygens. So this double bond, it is resonating between these three oxygens. So you can see here, so these are the resonance structures and this is the resonance hybrid. So this double bond you can able to show like this, it is delocalizing between these two oxygens. So this double bond is not fixed between these two oxygens. So this if you see here, so there is a two lone pair of electrons when oxygen forms a double bond, and when oxygen forms single bond, three lone pair of electrons are present. When shifting of this lone pair of electrons between these two oxygens, then what happens, this there is a single bond between these two oxygens. So that's why this double bond is delocalizing between these two oxygens. So this is a resonance hybrid of these two resonance structures. These two are called as resonance structures and this is called as resonance hybrid. The shape of molecule is angular, so with a bond angle of 117 degrees. So it is a bent shape it is having, or in angular shape we can call it as angular shape, and the bond angle is 117 degrees. And it is a resonance hybrid of two main forms. So these are resonance structures and this is the resonance hybrid, right children? So this is about the structure of ozone. Next, coming to the uses of ozone. So as we know that ozone, it gives nascent oxygen, so it is having oxidizing capacity. So that's why it is used as a germicide and disinfectant and for sterilizing water. Okay, so it oxidizes the all microorganisms present in water, so it can able to it is used for sterilizing water. So it is also used for bleaching oils, ivory flour, starch, because it is liberating nascent oxygen, it is having oxidizing nature as well as a bleaching nature. Okay, so it acts as an oxidizing agent in the manufacture of potassium permanganate. Okay, so for the preparation of potassium permanganate, so it is used for the as a oxidizing agent. So these are the uses of ozone. So these are the topics that we have covered, children. So now let us see what we have learned till now. Dioxazine, so O2. So it's a preparation. We have seen laboratory methods. We have seen three laboratory methods. In that, first one is oxides of salts which are having oxygen, like chlorates, permanganates, nitrates. When they are heated in presence of catalyst, they give oxygen. For example, potassium chloride, when it is heated in presence of manganese dioxide, oxygen is liberated. And decomposition of hydrogen peroxide in presence of manganese dioxide and finely divided metals also gives oxygen. And thermal decomposition of metal oxides which are low in the electrochemical series, and higher metal oxides like Pb2O3. So when they are undergo thermal decomposition, they can give oxygen. So these are the laboratory methods that we have discussed in dioxygen preparation. And in industrially, it can able to prepare from water and air. In electrolysis of acidified water gives oxygen. And compression of air, and removing carbon dioxide and water, and then fractional distillation, it gives oxygen. So these are the methods of preparation of oxygen. And then we have discussed the properties of oxygen. So because oxygen, it reacts with most of the elements except noble metals and noble gases like helium and neon, but it can able to react with the krypton and xenon. Okay. And it form oxides like acidic oxides, basic oxides, or neutral or amphoteric oxides, it can able to form. And then we have seen uses. So in AC is acetylene oxy torches, it is used. And in oxygen cylinders, it is used for the combustion of fuels also. Oxygen is very important. Next, simple oxides we have seen. So types of oxides: acidic oxides, basic, and amphoteric, and then neutral oxides. Okay. And ozone preparation. So on passing the stream of oxygen, dry oxygen through a silent electric discharge gives ozone. Okay. And in that properties we have discussed. So this ozone is having oxidizing property. It has a change sulfide to sulfates, iodide to iodine. Right, children? Structure of ozone, it is having a angular structure, and it is having two resonance structures and one resonance hybrid it is having. Next, after that, we have seen uses, because it is used as a germicide and for sterilizing of water. So ozone is used. Okay. So I think you have understood. Well, children, follow the class and write the notes. Thank you, ma'am, for this opportunity.
Thank you, Madhavi ma'am.
Thank you,
Indeed,
ma'am.
it was a very wonderful presentation today by you. So you have very clearly explained about all the properties of like oxygen, and also about ozone and how is it prepared. See, dear children, ma'am has very clearly explained you regarding the preparation of ozone and the oxidation properties of ozone. So you'll get an 4 marks question from this chapter, children. Like you'll have a split of 8 marks, means you'll get 2 4 marks in that. Sometimes they will be asking what are the oxidation properties of ozone, and they will combine another question from either fifth group elements or from seventh group elements. So this is a set of combination of different families like nitrogen family, oxygen family, and then halogens.
Halogens.
So please watch our YouTube channel, children. So please write down the notes and follow our classes, so to strengthen your subject and knowledge. So I thank Madhvi ma'am for her
Thank you, ma'am.
efforts to make this wonderful webinar. And
Thank you.
we thank each and everyone for giving us this great opportunity.
Thank you, ma'am.